Hello and welcome to another episode of Interactive Biology TV, where we're making biology fun. My name is Leslie Samuel, and inside this episode, episode 24, I'm going to be talking about how myelin sheaths increase the speed of the action potential. And this is actually in response to a question that was asked by NicoDoob23 on YouTube. I'm not sure if I'm saying your name right, but if I'm not, please forgive me. This video is in answer to the question that you left. And his question was placed on episode 15 on YouTube, where I spoke about saltatory conduction. And this is what he says. He says, but why would the steps be bigger in myelinated versus unmyelinated axons? That's the real question. What is the conceptual explanation for insulation increasing speed of conduction? That is an excellent question, such a good question that I felt the need to make this video to answer the question. So this is what he's referring to. Here we have a neuron, and the axon has these myelin sheaths. So I'm going to write here, myelin sheath. And those are made by the Schwann cells. This is a Schwann cell that's actually surrounding the axon and forming that myelin sheaths. And with saltatory conduction, I spoke about how the action potential jumps from one node of Ranvier to the next node, to the next node, to the next node. I called that saltatory conduction. And I said that is responsible for speeding up the signal. Since you're taking bigger steps, it's going to travel faster. So what I want to do is explain how that happens. When a stimulus comes along and causes the membrane potential to reach threshold, I said that voltage-gated sodium channels open. So I'm going to say this is a sodium channel. We know that we have a bunch of sodium ions on the outside, and when those channels open, sodium is going to rush in. When sodium rushes in, it doesn't just stay here. Sodium has a positive charge, and that's going to cause the positive charges that are close to it to be repelled, and sodium is actually also going to rush down the axon. Now, this process of the charges moving along the axon, this is called electrotonic conduction. So what you have is a positive charge moving in, repelling all of the other positive charges, and the positive charges are just traveling along the axon. One of the main benefits of this type of conduction is that it's extremely fast. Okay, and that's a good thing. You want it to be fast. However, we can't rely solely on electrotonic conduction. The reason for that is this also dies down. Okay, so the charge dissipates. So let's say the threshold is negative 55 millivolts. Membrane potential reaches the threshold. Sodium rushes in, causing it to become very positive. That positive, I'm going to put some pluses here. That positive is going to repel the other positives, and those charges are going to move along the axon extremely fast. So let's say it goes down here, it goes down. However, as it moves, that charge dies down. And if we were to rely only on electrotonic conduction, if we have a long axon, the signal wouldn't reach all the way to the end because it would die down and die down until it gets beneath the threshold. That's a problem. So what we're going to have here is, right here we have more voltage-gated sodium channels. We actually have them all along, but here they're covered up. So even though there's sodium ions on the outside, they can't get in because these sodium channels, the voltage-gated sodium channels here, are blocked. So as the charge moves down and it dies down, before it dies down too much, we have more voltage-gated sodium channels here, and those voltage-gated channels are going to open, and of course, sodium ions are going to rush in. They can move, again, the charges can move via electrotonic conduction. Before it dies down too much, we can have more sodium ions rushing in here. and charge moving down by electrotonic conduction. Now the problem with this process is that it's much slower. And if we were to rely on the voltage-gated channels opening to cause the action potential to go all the way down the axon, that would take much longer. And of course, you know, if you put your hand on a hot stove, for example, you want that signal to travel extremely quick. The good thing here is that it helps to increase the membrane potential. So I'm going to put an arrow going up, and E sub M stands for membrane potential. That causes a boost in the signal so that this process can continue. So we have an exchange of this fast process with this slow process. Fast process, slow process. But the way it's paired makes it so that the signal can jump quickly from one node to the next node, to the next node, to the next node. So Nicodube, to answer your question, the reason why it makes it faster is because electrotonic conduction is fast. Voltage-gated sodium channels opening is slower. So we're pairing them up so we can have a combination, the perfect combination of a fast-moving charge and a boost to the membrane potential so that fast-moving charge can continue, another boost to that membrane potential, fast-moving charge can continue until we reach all the way down the axon. I hope that makes sense to Nicodube and anybody else who has questions about saltatory conduction and how the myelin sheaths increase the speed of conduction. That's it for this video, and I'll see you in the next one.